Hello, everyone. My name is Shamik Sarkar, and I'm a postdoctoral scholar at UCLA, working with Professor Daniela Cabrick. However, the work that I'm going to talk about today was done during my PhD at the University of Utah, where I was supervised by Dr. Sneha Kasin. Part of this work was also done at the Nokia Bell Labs, where my mentor was Dr. Milind Buddhikot. Okay, so today I'm going to talk about DeepRadar, a deep learning-based environmental sensing capability sensor designed for CBRS. The FCC has announced a set of rules known as CBRS for spectrum sharing in the 3.55 to 3.65 gigahertz band. CBRS is important as it opens a 100 megahertz band for commercial wireless usage. The Department of Defense Naval Radar are the incumbent users of this band, and the mobile network operators are the secondary users. When radar signals are not present, this band can be used by the mobile network operators. However, in the presence of radar signals, the band occupied by radar must be released. A key enabler for this idea is the Environmental Sensing Capability, or ESC sensor. The ESCs are to be placed along the US coastline for detecting the presence of radar signals. The design and implementation of an ESC pose several challenges. First, the radar transmitter emits low duty cycle pulses while being mobile and rotating their antennas 360 degrees. The radar transmitter location, its transmission parameters are also unknown, and they may appear at unknown times. Thus, the ESC must continuously monitor the 100 MHz CBRS band with high temporal resolution. Second, the ESC must accurately estimate the bandwidth of the radar signals. This is essential for incumbent protection as well as efficient spectrum sharing. There are 5 different types of radar signals with bandwidth in the range of 1 to 100 megahertz that can appear anywhere on the CBRS band. This slide shows the power spectral density of 2 different types of radar signals. Third, the ESC must detect the radar signals not just in noise, but also in interference of unknown characteristics. The interference is from the LTE base stations acting as secondary users. Our objective in DeepRadar is to design an ESC system that solves all of these challenges. DeepRadar is a novel deep learning-based system for detecting radar signals and estimating their spectral occupants. It makes decisions in real time and maintains continuous operability. DeepRadar adapts its computations based on the available computing resources, and it can tackle interference of unknown characteristics. We use a learning-based approach because traditional signal detection techniques are inadequate for solving the challenges of an ESC. For example, energy detection cannot distinguish between radar and interference if they are of comparable energy. Match filtering requires knowledge about radar pulse shape, which is not possible because the radar pulse parameters are unknown and variable. In contrast, using a learning-based approach, DeepRadar can learn diverse patterns that accurately characterize the radar signals. Furthermore, DeepRadar can jointly solve the problems of radar detection and their bandwidth estimation. DeepRadar comprises of 4 constituent elements, as shown in this slide, and now I will talk about each of these components. The input to DeepRadar are the IQ values obtained by sampling of the captured RF signals. DeepRadar divides these IQ values into contiguous observation windows, each of duration TO, and produces a decision or prediction for each of these observation windows. The central component in DeepRadar's decision-making is the spectrogram image learning, or SIL. Let us see how SIL works. First, we subdivide an observation window of duration TO into smaller time slots of duration TS, as shown here. For now, I am hiding this adaptive computing block, but I will bring it back later. Then, for each of the smaller time slots of duration TS, we compute the power spectral density, which involves FFT computation. Then, we stack up the PSDs for different time slots and create a 2-dimensional image or spectrogram. Next, we make an important observation. The radar pulses create bright spots on the spectrogram. Now, if we consider all the bright spots on the spectrogram as a single radar object, then this red rectangle gives us the location of the radar object on the image. Further, the width of this rectangle gives us the bandwidth of the radar signal. Thus, our purpose of radar detection and their bandwidth estimation will be served simultaneously if we can detect and localize these radar objects accurately. And this can be done via object detection used in computer vision. For object detection, we use a simplified version of YOLO. YOLO is faster than other object detection methods because it requires a single pass of the input spectrogram through a single convolutional neural network. The basic idea of YOLO is to define objects in terms of tuples of size 4. For example, here, this object is defined in terms of X, Y, W, and H. Then YOLO uses a CNN as a regressor to estimate the size 4 tuples for each of the objects. We use a simplified version of YOLO because our object detection task is simpler than the general object detection problem in computer vision. For example, as discussed in previous slide, YOLO uses tuples of size 4. However, SIL uses tuples of size 2 because we only care about X and W that define radar center frequency and its bandwidth. Simplifying the object detection task reduces the size of our CNN and consequently SIL's prediction time, which is important for continuous operation of the ESC. At a high level, the object detection problem is a regression problem that minimizes the mean square error loss function. This equation shows the different types of errors that we are minimizing. The localization error measures the radar center frequency and bandwidth estimation error. The misclassification error is the classification error of radar signals, and the confidence errors measure the gap in confidence in detecting radar signals. Next, let us look at this block, which decides the dimensions of the spectrograms. The width of the spectrograms depends on the length of the PSDs, and the length of the PSDs depend on the time slot TS. We determine that there is a constraint on TS and derive that we must have TS less than equals to 4.096 microseconds to achieve high radar detection accuracy. The basic idea is that the detection accuracy depends on the brightness of the spots, and the brightness of these spots depend on TS. Once we have decided the width, the height of the spectrogram depends on the observation window, TO. Based on the properties of radar signals, we select our observation windows to be of 13 milliseconds. Next, let us look at this block, the adaptive computing block. The IQ values for different time slots are fed into a memory buffer. This buffer is cleared by the PSD or FFT computation. Now, given that our sampling rate must be high, above 100 megahertz, without this adaptive computing block, this buffer may overflow if the FFT computations are not fast enough. So in adaptive computing, we address this problem using the following approach. First, we compute the energy of all the n time slots in an observation window, and then select T out of the n time slots having highest energy. Then we compute the power spectral density only for the selected T time slots. We select the time slots with higher energy because they have higher possibility of containing radar pulses. And computing lesser number of PSDs leads to faster clearing up of the buffer. We call this strategy skip. Our skip strategy is based on the observation that even after selecting a window of 30 milliseconds, there is still temporal sparsity in the spectrograms. The skip technique attempts to reduce the temporal sparsity in the spectrograms. For example, this slide shows a spectrogram before skip on the left and after skip on the right. Our skip strategy is adaptive because different hardware has different computing resources, and DeepRadar adapts the number of skips based on the available computing resources on the ES. Next, let us see how DeepRadar tackles unknown interference. The interference is unknown because multiple LT signals operating on the same band may aggregate at the ESC as shown in this figure. Along with that, different LT base stations may have different and unknown uplink downlink configurations. The unknown interference can create unknown image background in the spectrograms and jeopardize the radar object detection. To solve this problem, we first determine that the unknown interference can be broadly categorized in two types: random and non-random LT interference as shown in this slide. In case of random LT, there is no temporal or spectral pattern. And in case of non-random LT, there is some spectral pattern, but no definite temporal pattern. Based on this finding, we use a data augmentation approach for dealing with unknown LT interference. We use some over-the-air LT data and synthetically generate spectrograms with various random and non-random LT patterns. Then we use these artificially generated patterns and augment our training dataset for training SIR. Now let us move to the evaluation of DeepRadar. For data collection, we use this setup shown in this slide, where one signal generator is used for generating data signals and the other one for AWG and interference. The generated signals are combined using an RF power combiner, which is then fed to the ESC. In our setup, the ESC sensor is an ALT software-defined radio. I'll talk more about this sensor later. Finally, the ESC output are written into files that are later used for training and testing. During data generation, we randomly vary the radar and interference parameters across examples. The generated data is randomly divided in training and test set. For our evaluation, we use this criteria. PC is the classification accuracy, PD is the radar detection accuracy, PF is the radar false positive rate, BWM and BWE are the average radar bandwidth missed and average radar bandwidth estimated in excess. For comparison of DeepRadar with existing methods, we use these 5. I'm not going into the details of these methods, but at a high level, the energy detection method is a non-learning method, whereas the remaining ones are learning-based methods. And among these 5, only the multi-channel CNN can estimate the radar bandwidth. It does so by dividing a spectrogram in 10 smaller sub-images and running them through a trained CNN for signal classification. Thus, the radar bandwidth in MCNN is estimated in multiples of 10 megahertz. First, we evaluate SIL for different values of signal to interference ratio and for all 5 radar types. Here, SIR is an abbreviation of peak signal to average interference ratio. We have the SIR values on the x-axis and the classification accuracy on y-axis. We observe that the classification accuracy is above 99% for all 5 radar types when SIR is above 20 dB. For SIR values below 20 dB, the accuracy for radar type 1 is affected most. This happens because radar type 1 is the most difficult one to detect with a pulse width as small as 0.5 microseconds. Next, we compare SIL and MCNN in terms of missed and excess bandwidth. We have the different radar types on x-axis and the missed bandwidth and excess bandwidth on y-axis. We observe that MCNN's missed bandwidth is slightly higher than that of SIL. However, MCNN's excess bandwidth is significantly higher than that of SIL. This happens because MCNN can estimate the radar bandwidth only in multiples of 10 megahertz. Next, we compare DeepRadar with other methods for all 5 radar types. We show the results for 2 different values of SIR, 20 dB and 25 dB. We have the different methods on the x-axis and the classification accuracy on y-axis. For radar type 1, the energy detection and HSBM methods have inferior performance compared to the other methods, and the accuracy of the remaining methods is comparable. For radar type 2, the observations are similar. However, in this case, the energy detection and HSBM methods have better performance compared to radar type 1. For radar type 3, all methods perform well, and the accuracy is above 98%. As in radar type 1 and 2, energy detection and HSBM methods are inferior than others in radar type 4. Similar to radar type 3, for radar type 5, all methods have comparable performance, and the accuracy is above 98% at 20 dB SIR. By summarizing the last few figures, we can say energy detection and HSBM methods have poor performance for radar type 1 and 4, so they are not usable. The remaining 3 methods, our proposed SIL and APCNN and PSVM, are comparable. However, APCNN and PSVM cannot estimate the radar bandwidth. Instead, in contrast, SIL has 99% radar detection accuracy at 20 dB SIR, and it can also estimate the radar bandwidth accurately. Now let us see the implementation details of DeepRadar. We designed DeepRadar as a 4-process pipeline. As shown in this slide, the IQ process streams the IQ values from the RF front-end to the memory unit on the compute node. The energy computation process takes these IQ samples and computes the energy of the time slots for adaptive computing. Based on the computed energy, the spectrogram formation process computes the power spectral densities and forms the spectrograms. Finally, the CNN takes the spectrogram and produces the final output. For implementing this pipeline on a commercial software-defined radio, we investigated the suitability of 5 different SDRs. We determined that only the X310 and ART can be used. For an X310-based implementation, we need a server-class machine connected to the X310 SDR via a 10 gig Ethernet cable. In contrast, the ART eliminates the cabling between the RF receiver and the compute node by placing an RF transceiver and an NVIDIA Jetson TX2 on the same circuit board connected via PCIe. The Jetson TX2 acts as the compute node. The TX2 is a GPU-enabled embedded edge computing device with shared memory. We use the ART software-defined radio in our implementation. Using our implementation, we test DeepRadar with different types of interference signals. We observe that our implementation has close to 99% accuracy for all 5 radar types and for different types of interference. This slide also demonstrates that our implementation can meet the ESC certification criteria, which requires more than 99% accuracy in terms of radar detection at 20 dB SIR when the interference is AWGN. To summarize, we presented DeepRadar, a novel and adaptive deep learning-based ESC system. We showed that DeepRadar outperforms existing approaches. We implemented DeepRadar on commercial software-defined radios, and our implementation can meet the ESC certification requirements. With that, I will stop for questions, and thank you for your time and patience.